To look deep inside the human body without using a scalpel, we have to start with a violent subatomic collision. The light we use every day to navigate the world has strict limits. Visible light vibrates at a frequency between 4 and 7 times 10 to the 14th hertz. At that specific rhythm, light waves simply bounce right off the surface of human skin. To see what lies beneath, we require an entirely different class of electromagnetic wave. When scientists first managed to harness this penetrating wave, the result looked like this. By capturing the shadows cast by solid bone and a heavy metal ring, they proved that solid flesh could be rendered transparent. Generating these images requires pushing the fundamental laws of electromagnetic physics to their absolute limits. The theoretical foundation for those laws was established by a Scottish physicist named James Clerk Maxwell in the 19th century. Maxwell's equations laid out a rigid set of rules. A stationary of electrical charge produces a steady electric field. A steady current of moving charges produces a steady magnetic field. Neither scenario generates a wave. To trigger an electromagnetic wave, a charge must undergo a sudden change in speed. It must be actively accelerated or decelerated. When a single charge speeds up or slows down, it creates a ripple effect. This action produces an oscillating electric field in space, which generates an oscillating magnetic field, which in turn acts as the source for another electric field. They regenerate each other, propagating outward as a self-sustaining wave. The energy of that resulting wave is directly tied to the violence of the charge's acceleration. Generating a wave with enough penetrating power to pass completely through human tissue requires subjecting an electron to extreme physical forces. To manufacture forces of that magnitude, early researchers relied on hardware that operates as a microscopic firing range. Inside an X-ray tube, a concentrated beam of high-energy electrons is fired directly at a dense metal target. When that high-speed electron slams into the densely packed lattice of metal atoms, it experiences massive, rapid deceleration. The kinetic energy lost by the braking electron has to go somewhere. It is instantly converted into a high-energy electromagnetic wave. This chart shows the complete electromagnetic spectrum. Because the physical braking is so abrupt, the resulting wave has an incredibly short wavelength, falling anywhere from 10 to the -8th down to 10 to the -13th meters. This places it far beyond the ultraviolet region. X-rays are the literal shock waves of subatomic car crashes, possessing frequencies far beyond human perception. The exact physical properties that make these waves invisible to our eyes also make them a perfect medical diagnostic tool. Because their wavelengths are infinitesimally short, X-rays slip effortlessly through the wide gaps of loosely packed molecular structures, like skin and muscle. But when the wave hits dense, tightly packed material, like calcium-rich bone, it cannot pass. The high-frequency waves are completely absorbed and blocked. This differential absorption creates the precise shadow map doctors use to locate internal injuries. Yet, that penetrating power comes with a severe biological cost. If human tissue is overexposed, the extreme energy of the X-ray can literally strip electrons away from healthy atoms, a mechanical disruption known as ionization. Stripping those crucial electrons physically damages living cellular structures and irreparably mutates DNA, leading to severe long-term health risks. Harnessing subatomic collisions gives us the power to heal from the outside in, provided we respect the high-energy physics capable of doing the same damage to ourselves.